All right, some more problems about graphs. Draw a regular graph with 7 vertices of degree 3, or explain why no such graph exists. Well, in this problem, our degree list would have to have 7 vertices, all of degree 3. 3, 3, 3, 3, 3, 3, 3. The sum would be 21. I have 7 vertices of degree 3. That's odd. And if we recall from the very last example in the previous assignment, the sum of elements in a degree list has to be even. So there is no such graph. All right, we should be so lucky that all our problems are impossible. Draw a regular graph with 10 vertices of degree 3, or explain why no such graph exists. Well, now, since I have 10 vertices of degree 3, the sum of the degree list would be 10 times 3, or 30, which is even. So possibly such a graph does exist. So let's try. 10 vertices, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Now I just want all of them to have degree 3. Okay. So let's make all of them have degree 2 by making a nice little wheel. Okay, we want all of them to have degree 3. So if multi-graphs were allowed, we could do a nice like chemistry-looking example by perhaps doing something like this. So now every vertex has degree 3. We don't have to make a multi-graph to do this, however, so I'm actually just going to erase those edges I put in. We can do this without doing a multi-graph just by doing, for example, let's have everything connect straight across. Okay, there isn't a vertex in the middle, it's just all the edges happen to be crossing there. But there we have it, 10 vertices, all of degree 3. 9 vertices of degree 4, okay? 9 times 4 is 36, it should be possible. 1, 2, 3, 4, 5, 6, 7, 8, 9 vertices. Let me just make them bigger so our connections are going to be easier to spot. Degree 4. Again, if we were allowed to do multi-graphs and there was no requirement of connectivity, I could just put 2 loops on every vertex and have it be completely disconnected, but that wouldn't be terribly interesting. All right, let's start with, again, a nice little wheel structure. So now everything is going to have degree 2. I could put a loop on every single vertex, transforming them all to be of degree 4. But again, that would be a multi-graph, which isn't prohibited. It's a totally fine solution. But let's just try not to do it. Let's have everything go. There isn't something straight across, but I can go there and there. So now that has vertex. That vertex has degree 4. There and there. There and there. Let's see. This already has degree 4. This has degree 4. This has degree 4. This pattern should hold just fine. Four, 4, 4, 4. There we have it. Okay, so there is a perhaps prettier way of making a regular graph, 9 vertices of degree 4. We didn't need to make a multi-graph out of it. Okay, we want a connected graph with the given degree list that contains a complete graph on 4 vertices as a subgraph. Now, a complete graph on 4 vertices as a subgraph, I'm going to draw that first. 1, 2, 3, 4, and all possible connections between them. Okay, so all possible connections, there we go. So there are 4 vertices and K4 as a subgraph. Okay, now notice that the degrees are 3, 3, 3, and 3. So if I didn't want to have a connected thing, I could have that just be 3, 3, 3, and 3, and then make 2, 4, 4, 4 hanging off over here and not connect them. But this is supposed to be a connected graph. So the other vertices I put in, there's going to have to be a way to get from these other vertices to this subgraph. So I'm going to have to connect to one of these, at least one. meaning one of these vertices is going to gain a degree at least. Okay, so we've got 4 vertices down. We need a total of 8. So let's put 1, 2, 3, 4 other vertices around. Let's connect here and there. So maybe I'm going to get away with leaving this as degree 3, and degree 3. This now has degree 4. This has degree 2. So can I just make all the rest of these have degree 4? If I was doing a multigraph, but I don't want to have to do a multigraph, just as a matter of principle. So let's do there. So this now has degree 3. This vertex here has degree 2, so I need to connect it to something. Let's actually connect it like that. It now has degree 4, this has degree 3. This is still sitting at degree 2. Let's see, we want 2, 3, 3, 3, 3, 4, 4, 4. So we have an extra 2 and we don't have enough 4s. So you know what I'm going to do? If I connect these two, then this becomes 3 and this becomes 4. So let's just check. Here is my K4 subgraph. I started off drawing it because I knew I wanted it in there. And then all of my connections are legit. Let's check all our degrees. 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3. I'm just counting edges leaving. 1, 2, 3, 4, 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2. 2, 3, 3, 3, 3, 4, 4, 4. Okay, there we have it. Again, many, many ways you could do this. This just happens to be one way that you can do it. And now we're tasked to make a connected simple graph with a given degree list. Then we're supposed to label edges and vertices and find an Eulerian trail. So previous examples didn't require us to make a simple graph. I just chose to do it, but now it is required. And an Eulerian trail is going to be a trail that goes through the graph and uses every edge exactly once. So since we know we have to label the vertices at the end, I'm going to start off by just making all of my vertices labeled. We need 6 vertices, so let's just use letters A, B, C, D, E, F. We need to make this connected, and the degree list is 2, 2, 2, 4, 4, 4. Now if I start off with this wheel arrangement, everything will have degree 2. I then need to add to 3 vertices, and if I just make like a sort of sub-triangle in here, so now my degree list is 2, 2, 2, 4, 4, 4. It is a connected graph. It is a simple graph. All right, now we're supposed to label each edge and vertex. Well, the vertices are already labeled. If we just want to label the edges, this is the edge connecting A and F. It's undirected, so I'm just using sets, not ordered pairs. A, B, B, C, C, D, D, E, etc., etc. This part is just kind of reminding us what the notation is. It's not a particularly interesting bit here. And AC. Okay, all of the edges have been labeled. Awesome. Find an Eulerian trail, or explain why there is none. So the way we know that there is an Eulerian trail, there's an Eulerian trail in a connected graph if and only if there are either 0 vertices of odd degree or there are exactly 2 vertices of odd degree. We do not have any vertices of odd degree, which means it's actually possible not just to make an Eulerian trail, but a cycle. So it's going to end exactly where it starts. And honestly, it doesn't matter where you start. So let's start at vertex A. Then we'll use the edge AB to go to vertex B. Let's actually just go all the way around the outer wheel. That's going to bring us back to A. So far what we've done is we've gone from A to B to C to D to E to F back to A. So we have used up all of these outer edges. In an Eulerian trail, we don't want to use any edge more than once, so I'm not going to go through any of these again, but we do have to use every edge, so I need to use these things down here. So we're currently at A, so let's just go to C to E and back to A. So let's just check. A, B, C, D, E, F, A, C, E, A. A, B, C, D, E, F, A, C, E, A. It goes across every edge exactly once. There it is. Basically the same as the last problem, except here it's got to be a multigraph. The degree list actually tells us this because there are 1, 2, 3, 4, 5 vertices, but this one has degree 6. So there have to be vertices that it connects to more than once. Okay. So since we want to label everything, we'll start off. There are 5, so I'm just going to go with A, B, C, D, E. Let's go ahead and start off with one of these outer wheel structures. Now everything has degree 2. If I go ahead and do something like now these two are the only 2 vertices remaining that have degree 2. So and I need 2 vertices with degree 2. So let's go ahead and leave those. And we're allowed to do a multigraph, so currently this is sitting at degree 3, and degree 4. I need to increase this by 1, increase this by 1, increase this by 2. I shouldn't say need, that is one viable solution. I could, for example, leave this at degree 4 and just worry about manipulating those, but if I just double up this edge and double up this edge, and since we're making a multigraph, that's fine. This now has degree 4, degree 4, degree 6. So we've got a connected multigraph with the given degree list. Find an Eulerian trail. Oh, so we're supposed to label the edges. Okay, so since this is a multigraph, this is the edge AB, but it's the first one. This is the edge BC, but it's the first one, etc., etc. This is a terribly uninteresting part of the problem. It's just a notational reminder. So we would keep going around. Let me just erase those degree markings. They're getting in the way. Okay, we do have all the correct degrees. Okay, blah, blah, blah. A, E, they're undirected though, so those are sets. It's the first one, A, E, sorry, E, D. In set, I can put it whatever order I want. It's the first one, D, C. It's the first one. In the interior, we've got AD, but there's a first one and a second one. And here there is AC, a first one, and AC, a second one. Sorry, that's really bad writing because it got a little crowded. Labeling the edges is not terribly interesting. Okay, in fact, to make the Eulerian trail more clear to view, I'm actually going to erase these edge labels. They're not really all that instructive. Okay, they're included as part of the exercise just to remind everyone that there is this notation, but it's not all that important. We don't generally write out our trails by actually labeling the edges. We just say go from one vertex to another by using an edge that connects them. And since we're attempting to do an Eulerian trail, the assumption is use an edge you haven't used before. Okay, so since there are no vertices of odd degree, it is possible to do an Eulerian trail. And in fact, since there are no vertices of odd degree, it's possible to make it a cycle. Let's go all the way around the outside, A, B, C, D, E, back to A. So at this point, we have used up all of the edges on the outside, and we're back at A. So either I'm going to go to D or I'm going to go to C. Let's just go to D. So at this point, we've gone all the way around to D. We can't use any of these. So the only thing, having gone from A to D, is to go back to A on the other edge connecting them. And then I've got 2 edges, but they both connect to C, so go to C and then go back. So following, we go all the way around, A, B, C, D, E, A, to D, and then back along the other edge connecting them, and then to C, and then back along the other edge. So this uses every edge exactly once. All right, same. We got 6 vertices, A, B, C, D, E, F. Degree list 222, 334. I've been doing a lot of graphs where I just start by making the wheel arrangement on the outside, so let's not. Let's start off with something like this. Okay, this already has degree 4, which is the largest degree I want, so we'll stop adding stuff to vertex E. But I can maybe do that. And that. So let's check. This is 3, 2, 3, 2, 2. 2, 2, 2, 3, 3, 4. Great. There are tons of ways this could be done. Doesn't really matter. I'm going to erase the vertex degrees because it checks out. Everything is fine. This one down at the bottom is vertex D. I didn't write it very clearly. There we have it. There are 2 vertices of odd degree. So it is possible to make an Eulerian trail. It will not be a cycle. It will have to begin at one of these and end at the other. So F and B were the 2 vertices of odd degree. So I have to start at one of them and I will necessarily end at the other. So let's start at F. From F, where do we want, oh, I didn't label the edges. Okay, it's really not very interesting. It's just undirected. So again, this would be, for example, AB. This would be the edge BE, et cetera, et cetera. Labeling the edges, I'm not even going to bother doing here. If this was one of your assigned problems, you should do it, but it's just not worth our time. Just label them. Okay, so now let's make our Eulerian trail. So we have to start at one vertex of odd degree and end at the other. I'm choosing to start at vertex F, which means I'm going to end at vertex B, the other vertex of odd degree. So from F, let's go to E. So now what we've done is we've used this edge here. So as we use edges, I'm just going to put a little tick mark through them. So we've gone ahead and we've used that. We're now at E. Let's go to D. We've used that. Our only choice now is to go to C, and we've used that. Our only choice now is to go back to F, and we've used that. So we're back at F, but we've already used this edge and this edge, so our only choice is to go to B. We've used that. Now all we have left is this triangle. It doesn't really matter what order we do it in. We're currently sitting at vertex B. Let's just go to E. We've used that. Our only remaining edge connecting to E goes to vertex A. So we've used it, and the only edge leaving A that we haven't used goes to B, and we're done. So F to E to D to C, back to F, to B, E, A, B. And notice we used every edge exactly once, and we had to start at one odd degree vertex and end at the other. Okay. We chose to do it in this, and it is abstractly true that that is the only way to do it, but this is just a bunch of exercise solutions, so we're not worried about proving anything here. And finally, a similar problem. Construct a connected multigraph with degree list 2, 8, 10. With so few vertices and such large degrees, we're going to need a multigraph to do this. Label each vertex edge, provide an Eulerian cycle that begins and ends at the vertex of degree 8. So since every vertex has even degree, this is doable. I only need 3 vertices, but I do need a lot of edges, so I'm going to separate them quite a lot. Just in terms of physical space, let's put A, B, C. There are my 3 vertices. One of the vertices is of degree 2, so let's not draw anything else to vertex A. So everything else goes between vertex B and C, or there's loops. So let's just put some edges between them. 1, 2, 3, 4, 5, one more of them. So right now we're sitting at degree 2, 6, and 6. So let's put a single loop here, and let's put 2 loops there. So our vertex A has degree 2, B has 1, 2, 3, 4, 5, 6, 7, 8, and C has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, so this checks out. The fact that I have a single vertex of degree 2 and it has to be connected means part of this is kind of locked down. The only real choice here is how many things go back and forth combined with how many loops. Okay, now we could label all of these edges. That would be very tedious. I'm not going to bother. Provide an Eulerian cycle that begins and ends at the vertex of degree 8. Well, that's B. So let's use the loop first, and then let's take care of the edge. So we've used the loop, then we went to A, then we went to C. So all there is to do now is go back and forth between C and B and use up some loops. So let's use up both of the loops. Now I'm back at C, so I go to B. I've used that. I go back to C. I've used that. I go back to B. I've used that. I go back to C. I've used that. I go back to B. There. So from B to B, so I do a loop. To A to C, use up both of those. To C, loop, loop. B, C, B, C, B. B, C, back to B, to C, to B. So there we have it. We've used every edge exactly once, and we began and ended at the vertex of degree 8. Multiple different solutions here depending on how you draw your graph. A lot of it's going to have a similar kind of feel to it, though.